Hi everyone, here we go on day 2 of chapter 11. Just a couple more things to cover before we call it for thermodynamics. Then we'll get to do a little bit of kinetic theory, which is going to involve a small tiny bit of stat mech, which should be interesting. You'll get a taste for that, and then we move on to kinetics. So that's kind of exciting. I've got a pretty bad case of cabin fever today. I've been stuck indoors for, I guess, 2.5 weeks now. I'm sure you all are feeling exactly the same way. I'm sure that everyone's really sick of just being indoors all the time. So I may go for a run a little bit later, and I think that'll help quite a bit, but figured I'd do 1 or 2 of these videos before I go do that. Here's what we're going to be talking about today. I want to talk about, we'll review what we talked about last time. We'll get to how to calculate the electromotive force or the voltage of a cell. Then I'll show you briefly how to calculate the Gibbs free energy from that electromotive force for a cell. We'll review the cell nomenclature for an electrochemical cell that you learned in general chemistry. We'll see a comparison between electrical and thermal work. And then we'll see some of the examples of reactions that are occurring in common household batteries. Okay, first remember we talked about Faraday's constant, usually indicated with the symbol F, and that's 96,485 coulombs per mole of protons, and that number is negative for mole of electrons. We saw the electromotive force, which is the voltage that's going to be imposed by an electrochemical cell. We saw how electrochemical cells have 2 half reactions, so they have 2 compartments in which different reactions are occurring. One is going to be releasing electrons, the other one will be accepting electrons. And the anode, we didn't cover this in last lecture, but the anode is the negatively charged terminal, so that's the one that is giving up the electrons. And an oxidation is recurring on the anode. The cathode, the positive terminal, that's the one that's accepting electrons. It's the electron destination, and a reduction is going on. One trick that I use to remember whether oxidation or reduction is happening at the anode versus the cathode is the anode begins with a vowel A, and oxidation also begins with a vowel O. The cathode begins with a consonant, and so does reduction. So that's how I am able to keep the 2 straight in my head. We saw how to relate the standard state electromotive force to the equilibrium constant. And then we saw an extension of that, the Nernst equation, which tells us for a given set of concentrations within an electrochemical cell, what is the voltage that's being imposed across those terminals. Okay, now let's take a look at these standard EMFs for a number of different half reactions. I'm going to now draw a complete electrochemical cell and we'll talk about it. So each of the half reactions are going to have a different E0 listed. And what those mean is that if the reaction was, the half reaction was put into one of these compartments, and then the reference reaction was put into the other compartment, which, remember, is going to be half H plus E minus in equilibrium with 1/2 H2, then this E0 would be the potential that would be imposed by the other reaction. Okay? So let's consider this reaction. Zinc 2 plus accepting 2 electrons from this wire. So let's say we have zinc 2 plus solution over there. And then it's forming solid zinc through a reduction reaction. Then that E0 is going to equal negative 0.7618. So that means that this reduction is actually going to cost voltage. It's not going to be a favorable reaction of its own. You would need a voltage imposed through some other means or through a stronger reaction in order to spontaneously cause that zinc to be reduced like that. Okay, so that's the E naught for a given half reaction. If we have a more complete reaction, like for instance this one, aluminum reacting with a zinc solution, and then that's going to reduce the zinc. I need to balance this reaction here. If we have this reaction, this is going to be composed of two separate reactions. We have the half reaction for the reduction of zinc, and the E naught for this one is negative 0.7618. And then we also can look up the reduction reaction for aluminum. That E naught is negative 1.66. Both of these are in units of volts. So in order to get the overall E naught for the entire cell, then we have to figure out which reaction is the one that's being converted to oxidation, and we need to flip that one around. And as you can see, this reaction is the one that is being flipped around to oxidation. Okay? So our overall cell electrochemical potential is going to be negative 0.7618 volts plus positive 1.66 volts. And you might be asking, why don't we multiply times the 3 and the 2 for the reaction? And the answer is because these E naughts are intensive quantities, and the stoichiometry, the stoichiometric coefficients don't actually matter in this case. So let's add those two together, and we find an overall cell potential of 0.8982. where it looks like my sig fig is that digit right there. Just a reminder, all these half potentials can be found at table 11.1 and 11.2 in the appendix in the back of the book. And in section 11.10, they actually list a number of different metals in order of most strongly reducing to most strongly oxidizing. So I'm just going to make a couple of interesting comments about this. Gold is the element that's the top of the most strongly reducing, and then platinum is not far behind it. And hopefully that makes sense, because in metal's metallic form, that's when it's reduced. And naturally occurring gold and platinum are going to most likely be found in their metallic form because they are such strongly reducing substances. So spontaneously, these compounds will reduce. That's why you can find veins of gold. Whereas in contrast, some of the most strongly oxidizing ones are lithium, calcium, potassium. All of those metals, you're never going to find their metallic form naturally occurring because they are just so strongly oxidizing. So I thought that was at least a fairly interesting aspect of the electrochemical series as it relates to naturally occurring minerals.